Welcome back to the fourth aspect of our taxonomy, which deals with so-called objective functions. Objective functions mean, translated in other terms, by which objectives or goals are the clustering results actually optimized. And while we had this one hyperparameter-oriented definition, we figure out now here what are the targets or the goals of each of these algorithms and what can be like identified in the end as one final outcome. So it is a result-oriented perspective on correlation clustering algorithms. We are not interested that in the code there are 2 for loops and we have here splitting into 2 data sets or whatsoever and merging and so on. But we are asking, just by looking at the results, which properties do the results fulfill or should they fulfill? And again, here will be a lot of formulas. I'm not expecting you to know all these formulas by heart, but to get these core messages, what they actually mean. And so here, for instance, we have Oculus and subspace correlation clustering. Both of them look quite similar, actually. And they are not really written like that in the paper. So this is something that I derived during my research in the previous years. So Oculus and subspace correlation clustering, what these 2 formulas mean, both of them minimize the distance of objects to other objects or to prototypes projected to cluster subspace. And this is, however, equivalent to minimizing distances orthogonal to correlation subspace. What does it mean? Well, once we have here the upper part, minimizing the sum of such distances, so minimizing the variance, you want to detect clusters in such a way that this axis is as small as possible. And this view is equivalent to this statement of minimizing the sum of such distances to that particular correlation space. So the core message is, if the objective of an algorithm, of a correlation clustering algorithm, is to minimize the orthogonal distance to this correlation subspace here, this is equivalent to minimizing the variance in the cluster subspace. This is the message, and both of them actually, they have as a goal to minimize like the deviation to the mean or to another object in this particular cluster subspace, which is equivalent to minimizing the deviation orthogonal to the correlation subspace. So this is the objective of Oculus and subspace correlation clustering. 4C and COPAC, however, do not have objective functions per se in terms of minimizing or maximizing specific aspects. However, what we propose here is to maximize the density over all clusters. So we say we want to have maximizing this expression, which means the neighborhood, epsilon neighborhood of an object should be as small as possible. And so a number of objects in the epsilon neighborhood of an object should be as large as possible. You want to have as many objects as you can in an as small epsilon range as possible. So you want to have a minimum of an epsilon range, having a lot of objects into it. Small surface or small volume, a lot of objects corresponds to high density. The same also for COPAC. Then we want to, here in case of 4C, minimize the deviation of objects orthogonal to correlation subspace. So the first one is increased density. The second one is minimize deviation orthogonal to the correlation subspace. This is here the second term that we have. So we say minimize this deviation that we have here. And in case of COPAC, minimize the number of required subspace to satisfy the explained variance, and which is corresponding to minimizing the deviation of objects orthogonal to correlation subspace. So what in case of COPAC you want to do, you want to minimize the number of required subspace. So you say, I wish to have like only one dimension if possible, if with this I can capture like 80% of the variance, for instance, or to minimize the deviation of objects orthogonal to a correlation subspace. So this is the consequence from this first statement. You want to have as many dimensions of your subspace as necessary, but not unnecessarily more, if you see you've got one direction, so in case you have one line which already captures like alpha equals 80% of your variance of your object scattered around that line, then you are happy with it. You do not want to have another dimension added to this. Then we have here cache. Also, cache per se does not have an objective function, so to speak, but also through other work we derived one. We say here for cache, also recently published last year at the ICDM workshop, we say the core goal of cache is, so this is the Huff space that you see, the linear, the Huff space of for detecting linear correlations. We want to maximize the density of a cell. So this is like a cell, this red box that you see here in Huff space. And by maximizing the density, it means, again, you want to have this box as small as possible while having as many functions as possible intersecting it. And having a smaller box means minimizing the deviation of objects to a subspace, because it means the alpha 1 upper and lower bound gets smaller, or alpha 2 upper and lower bound gets smaller. And this means we tolerate not that much of rotation, but we just tolerate a bit of rotation. The smaller, so large box, smaller box, smaller box, almost a point. This is like the intention by minimizing the volume of this box, of this cuboid. This is what we have here. And so this first term is like for the volume, and the second term is for the deviation or for translation that we actually have, because we say this volume is, so this volume is here. We want to keep these side lengths to a minimum, and also this one axis we want also to minimize, because here at V alpha, this volume is considered only for the angles that we have for the rotation, and we also need to cover the translation, which is here with this T delta. And so we want to minimize this box, which is composed of the side lengths of the alpha and of the delta. And we have here sonar as also one exotic way. Here the goal is to minimize the deviation of objects orthogonal to correlation subspace while minimizing model complexity. So sonar has a really interesting approach. They say we not only want to have the objects as tight around that plane or line as possible, but at the same time, we do not want to have unnecessary more and more subspace clusters. We want to have as many as necessary to be in a balance between number of clusters, and on the other hand, minimizing the deviation of objects to that particular plane. So in sonar, we have an interesting way through this MDL, this minimum description length approach, a balance between model complexity, which translates to number of subspaces and subspace clusters, and on the other hand, model accuracy, like reconstruction, or so how to minimize the deviation of objects to the subspaces. And we have LM class. LM class has also a different approach for the objective function. There the goal is maximizing the discriminability, which implies to minimize the overlap between two distributions. So you have like one distribution and you have like a second distribution of objects around a subspace. You want to keep those two distributions of these subspaces as minimized overlapping as possible. So in other terms, keep this overlapping area to a minimum. That is achieved by finding orientation and translation such that the distance between two means is maximized. So this mean and this mean, you want to keep this distance as far away as possible, while the variance of the two distributions is minimized, which is the denominator here. So you want this term here, this max G, maximum discriminability, means you want to keep the mean here and the mean here. Those two peaks you want to keep as far away as possible, while you want to have this variance. This blue one has a larger variance than the orange one. You want to keep them as small as possible. By increasing the nominator and decreasing the denominator, we got a maximization of discriminability, making those two to not overlap much. And at the same time, we have this depth, this J of tau prime minus J tau. This is actually here where you say you want to have the minimization of distances of objects to the subspaces. So this is what we have here. And now let us get to a conclusion. So what is the core message that we gain from the previous slides, or what can we say summa summarum? We say that correlation clustering algorithms have as a cardinal objective to detect subspaces in such a way that the deviation of these subspaces is either minimized or does not exceed a user-defined threshold parameter. So further, depending on the utilized algorithm, additional objectives may occur, such as increasing density, like in 4C, maximizing distinctiveness between clusters within a clustering, like an LM class, or minimizing model complexity, like SONAR with a minimum description length. But the core idea, so what we observe from these few algorithms and what you will also observe with all the other that you've seen in this one tree slide, these 12 algorithms, they all have as a goal to find clusters in such a way that the deviation is minimized or not exceeding a user-defined parameter. This is the core idea of the objective functions. So we can say, as a conclusion, correlation clustering has as a goal to find clusters in such a way that the deviation of objects to the respective subspaces is minimized, or that the density in the orthogonal cluster subspace is maximized. Those two are equivalent, as we've seen in previous slide. With previous slide, I mean this one here. So by minimizing the deviation here, it also implies that we maximize the density in this direction. Well, and this is it about the objective functions, and also about the tons of math that you've seen, or a lot of formulas that you've seen. But I hope that you get now this one core message of what correlation clustering or arbitrary origin and subspace clustering is optimizing towards. And see you in the next video then. Take care.